basically what's going up there now. Raphael. And no Matthew. Okay. Let's start out with any questions. All right. On the pre-course assessment, out of 30, the average was under 5. So you, for the most part, equally don't know anything, which is not unexpected at this point in the course. When you take it the second time, I expect it to be much improved. So, just to let you know, plenty to learn, or unlearn in some cases. That's not an unusual score. That's not the 110. I'm assuming not many of you, if any of you, have had physics before. Have any of you had physics before? High school counts. So high school physics?
Don't remember anything.
Okay. I think we last left off with how to express two-dimensional motion in vector form. Yes! The wait is almost over. All right, so we're dealing with a two-dimensional problem here. It's not like I think one of the examples they did last time is I had it at a tilt like that. Was that one of the ones they did last time? No? Okay. So let's first talk about, back up just a little bit. We were talking about having, say, 4 newtons and 3 newtons. It's a one-dimensional problem here. And so that's the net force of 7 newtons acting on it. I'm pretty sure we did do that last time. Right. Even in the blur, I'm seeing some nods. Or if I have a 4 newton to the right, 3 newton to the left, that's the equivalent of 1 newton to the right. So if we are at a tilt like this, under classic form, it's a two-dimensional problem. But this is a case right here where all we have to do is just change the axis. So I could just make that the I-hat direction. I'll make that 4 newtons. And so the total force is just 4 newtons I-hat. So it's still a one-dimensional problem. It's not like we have to do anything fancy for that. You can, if you are stuck with the horizontal vertical, then yes, you've made it more complicated, but you don't need to. But here we have an actual two-dimensional problem. And so how do you deal with it? We cannot get away with just a plus sign or just a minus sign as talked about last time. What we have to do is we have to define our coordinate system. And since this is to the right and up, why don't I just make those my coordinates? And I'm going to say to the right is I-hat, and up is J-hat. The total force is just sum. It's a sum of the forces. So my total force is, well, that force right there is 4 newtons to the right, or I-hat. This one is 3 newtons up, and up I said was J-hat. And we're done. That's it. It is not 7 newtons. Where I've broken this down into an I-hat and J-hat like this, this is known as rectangular form. Now, there's another form of it called polar form, which I at least want to touch on. To actually properly put it in polar form would require trig, and trig is beyond the scope of the class, so we're not going to go that deep into it, but I at least want you to see what polar form looks like. So I'm adding these two forces. When I add vectors, I add them head to tail. So I have 4 newtons to the right, and I have 3 newtons up. And I don't think I did this last time. Head to tail? No? Okay. So when you add vectors, you can add them graphically using head to tail. So I have 4 newtons to the right, 3 newtons up. That is a right angle there because they're perpendicular to each other. The sum is a vector from where we start to where we end. That is the sum of the two vectors. This is known as the resultant. Now the symbol I use for resultant, it is a vector. This is the one time I use the double print for some unknown reason. Now the magnitude of the resultant, how would you find it? That is within scope. How would you find the magnitude of this vector? I heard somebody start out saying it.
Oh, a squared plus b squared equals c squared?
There we go. What is that known as? Yep. Matthew?
Yes, sir.
I guess you have a choice of 2 seats.
I'll sit over there. Sorry, I got lost real bad on the way in here.
Well, glad you found it. And for Hannah and Matthew, what we did the last time, most of it was recorded and is posted so you can watch what you missed. All right, so it is a right triangle. It looks a lot like a right triangle. Technically, we're adding vectors, but geometrically, it's a right triangle. And so you would use Pythagorean theorem. The a squared plus b squared equals c squared. 3 squared plus 4 squared is equal to the hypotenuse squared. And so this will end up being 5 newtons. Again, that is within scope. Finding the angle is not in scope. I'm going to go do it very quickly. How many of you have had some trig in your lifetime? It looks like about 4 of you half-heartedly have had it. Okay. There's an angle right here. Trig is just about ratios. That if I have a 3, 4, 5 triangle, this angle is always going to be the same. So the tangent of theta is the opposite over the adjacent. And theta, you'll find, ends up being around 37 degrees. So properly, if I wrote this in polar form, I would write it as 5 newtons, 37 degrees. So this is polar form. When I wrote up the tangent bit there, if you're going, I've never seen that before in my life, don't worry about it. That might be the last time you see trig in this class. Unless there's a huge groundswell to do the trig version of this, and then I'd be glad to go into it.
You said the 5 newtons, 37 degrees is a polar form?
Yes, where you put the magnitude and the direction, that's called polar form.
And the 4n I top hat is the rectangular?
Yes. There are times when rectangular form just makes life easier, and times when polar form makes life easier. Questions at the moment?
do polar form, the only angle that you would need to know is the one that's opposite the 3 newtons on the right triangle.
The angle that you need to know is the one from the right horizontal.
Okay.
In this case, it happens to be opposite the 3, but it's always going to be, I talked about, you sort of established a coordinate system. There's one thing that I do assume is going to be true, is that 0 degrees, from your point of view, at 0 degrees, 90 degrees, 180 degrees, 270. And so the angle is always given from 0. It's positive angles this way, negative angles that way. So, okay. All right, I know you're trying to quickly get that stuff down. How close are you?
I got most of it.
Okay. And hopefully the video will have enough detail that you can pick up any little things. All right, so we've just touched on some vector mathematics just then. We did the addition of 2 vectors. Let's just go through, make sure that we're a little bit better on that. All right, so when you're adding vectors, head to tail method. Now the textbook does what they call the parallelogram method, which is a variation of the head to tail. Parallelogram method works fine if you have just 2 vectors, but if you're adding more than 2 vectors, it becomes a nightmare. But I am going to talk about the parallelogram method. Parallelogram method. Now, I did teach elementary school for a year, and I made sure that when I was teaching the little ones, that I wrote incredibly neatly. After I stopped teaching that, I thought, oh, I don't have to write neatly again anymore. But it does lead to some people constantly asking me, hey, what did you write right there? So please feel free to ask if you can't read my handwriting. So if I have a vector there and a vector like that, and I want to add them together, I'll just call this vector A, and I'm going to call that vector B. So I want to know what is A plus B. I am assuming that I have drawn the arrows appropriately, that vector A has a larger magnitude than vector B, just because that's a bigger arrow than that is. Using the graphing method, I take one of the vectors, and it does not matter which one. The commutative property holds. It doesn't matter the order in which I add them. I generally start with the first one, but I don't have to. And what I'm going to do is I'm going to pick a starting point, and I'm going to redraw that first arrow right there. And I want to draw it the exact same direction, exact same length. And so, as best I can, that should be the same length and same direction as the first one I drew. Or at least close enough given the fact that I'm writing on a board. Now I have a new starting point. Imagine that you're walking this. You're walking, that represents, let's say 20 steps in that direction. And then you turn, and now you're going to be walking 18 steps or whatever that would represent in that direction. So you're now here, and so now you're going to be walking this length right here. And so now, my resultant, my sum of these 2 vectors, is from where I started to where I ended. That is the resultant. the parallelogram method to do the exact same problem is you draw the two vectors, except you draw them tail to tail. So I'm going to pick my starting point there, and I'm going to take my A, that's my, should be the same length as, and direction as this one and that one. They should all be the same. I'm assuming in your notes you will draw it perfectly. And then you take B, and you draw it with a common tail. And then you draw a parallelogram. Those are the two sides. So I'm going to draw one up here that should parallel B, and I can't do that particularly well from an angle. I'm only marginally better straight on. That dotted line should be parallel to B. This one should be parallel to A. And not particularly well. Excuse my back. In the parallelogram method, the resultant is a vector from the common tail to the other corner. Mathematically, it's identical. It should get you the exact same results. And if you're adding two vectors, that's fine. We'll add three vectors, and I'll show you why I don't generally go with the parallelogram method. All right, questions up to here? All right, so let's add three vectors. So A, B, and, let's start over again. New letters, or new vectors. A, B, C. So I picked one of them, doesn't matter which one I pick. I'll start with A. Do a point, I'm going to do the head to tail method. I'm going to take that vector. As long as it's the same magnitude, same direction, we're considering the same vector, just like in the same vein that I consider those the same number. You may get into a philosophical argument some other time whether those are indeed the same number or just two different numbers with the exact same value. All right, so I have my new starting point here, and see, I want to draw some A so it doesn't, the letter doesn't get in the way. All right, so now here I'm going to draw B. There's B. And then I take the third vector, and I have a new starting point now. I'm going to take C. Draw that a little bit better. And my resultant is from where I started to where I ended. That's the sum of the three vectors right there. Questions here before I show how to do this with the parallelogram method? All right, so I take two of the vectors. When I'm doing parallelogram method, I have to start with two of them. So let's start with A and B. Why not? We could do, again, A and C. It really doesn't matter, or B and C. But so I'm taking A. I take B. That's A, that's B. Draw my parallelogram, so I'm something like that. I'm hoping you get the spirit of it, even if my drawing's off. A little bit better. So A plus B is this vector right here. That's A plus B. And now we're going to add C. Well, C is down and to the right. Lost it. That's not okay. So now I do a parallelogram between my A plus B and C. So that parallelogram is going to look a little bit like and so that is the final resultant right there. To me, it's a cluttered mess. So if you're adding more than two vectors, I strongly recommend head to tail, then parallelogram. And my resultants from the two cases are close. They're close. Sure, let's go with that. Questions to hear? We will talk about multiplying vectors when we get to chapter 7 and 8. There's two ways of multiplying vectors. We'll deal with this at that point. Oh, subtracting vectors. Let's just do A minus B here. We know what A plus B looks like, but A minus B? Well, subtracting is the same as adding the negative. I think we did one case like that last time. So A there's my A plus negative B. Well, B is going that way, so which way is negative B going? Let's see, one thumb pointing in the right direction, two thumbs. Can we get a third? There we go. And an index finger. Good enough. So that B is going the opposite direction. That's negative B right there. And so A minus B looks like that. That's pretty sure it's still called a resultant, but I don't know if the math people have a special name for it. Naveen.
What's the difference between A minus B and A plus B? It's the same, the result is the same.
The magnitude will be slightly different just because of the nature of the way I've drawn these two vectors. This is slightly smaller, but the other one is the direction is different. In order for two vectors to be the same, magnitude and direction must both be the same. And so this one looks like it's more like at a 45-degree angle, and that one's much closer to vertical. But now you have a worried look.
in the parallelogram method, would it not be the same, like vertical? Because that one, the top one is, the parallelogram,
Right,
but the other one is head to tail, the bottom one that you just drew?
this one right
No,
here.
no, yeah, the negative? No.
So, I missed the question then.
If you did the A minus B in parallelogram form as well,
Ah,
would it,
then you should get something like that. So A stays the same. B, you basically would then do negative B. And then a parallelogram is based on that.
oh, okay.
And so A minus B is A plus negative B, we're still going with that. And so that would be A plus negative B, which the math people tell me, is the same as A minus B. And it still goes back to a thing we had the last time, is that the negative vector just means other way. Opposite of what you're doing. Which is part of the reason why when we did the two-dimensional problem and I said I was to the right, I hat was to the right, I don't need to say what the direction of negative I hat is. If we know I hat is to the right, negative I hat has to be to the left. Right. Other questions at the moment? Other worries that I'm just not seeing? All right. Cool. All right. Let's get into some specifics. Let's talk about a specific vector quantity. How many of you have a force being applied to you right now? Only one of you. Two willing to admit it. And I'm not talking about emotional force or anything like that. We all have baggage. So there are a couple people who are willing to say they have a force acting on them. For those who raise their hand, what force are you thinking about?
Gravity.
Sitting on the chair.
Pardon?
Sitting on the chair.
What's the force?
Gravity and the chair acting on it.
All right, so I'm gonna, for both those answers, we'll get to the point where I'm gonna nitpick. I'm in the spirit of what you're saying, absolutely right, but we'll work on the language in a moment. Do all of you have a force of gravity acting on you? Not everyone is nodding, so some of you are not sure. What is another word for the force of gravity acting on you? There's an everyday word.
Weight?
Absolutely. So, all of you have a gravitational force acting on you. What is a force anyway?
Well, in the book it said a push or a pull.
Yeah, and that is the best working definition. There's a formal definition which is really horrible. The horrible formal definition is an influence which might cause acceleration. That really nails it down. Push or pull is what the definition I like. Now we are going to start out with the names of 4 forces for the course. There's going to be a 5th one, sort of a catch-all category, and as we go through the course, we're going to add a couple more But we're going to start out with 4 major forces, which will serve as a checklist. F-town, you've already gotten one of them, weight, or more generically, gravitational force. Weight is the gravitational force, is a specific gravitational force that we will use until we get to chapter 9 or 10, I can't remember which one. Either chapter 9 or chapter 10 is when we talk about a much more generalized gravitational force, but it's weight until then. The requirement. In order for there to be weight, there must be, I'll put this in quotation marks, one huge object and one small object. In other words, huge, I'm talking planet or moon, that size. And then small, something that you could see in one sight. I could stand there and look at it. If I can see the whole thing and it's nearby, that would be considered small. Gravitational force, the more generalized, all you need are 2 masses. There's a gravitational force between each of us. Any 2 people in here, any 2 objects in here, there's a gravitational force, but it's not called weight in that case. Weight, you require something planet or moon size.